Earlier we discussed linear motion and linear momentum and the forces that were acting on the fluid flow on a certain control volume. Now we try to review rotational motion and angular momentum, and we consider the forces that act in that situation. As we know, in a rotational motion, it's always indicated by, if it is cylindrical coordinates, by r theta z, and if it is spherical coordinates, then it is r theta phi. And if it is only two-dimensional, the motion that we are considering, then it's only r and theta that are under consideration. And the movement, the rotation, if the distance traveled is theta, then omega is assigned to the angular velocity, that is the angular distance traveled with respect to divided by time. So in linear velocity we have distance by time, in angular motion we have theta by t. So omega will be d theta by dt, and if theta is small enough, and it is considered here as small enough, it can be written as L over R, where L is the arc length and R is the radius of the circle in which the motion is taking place. So that is equal to 1 over R into dl by dt, which can be written as 1 over R into velocity v. So omega can be written as v over r, and that is the relation that we have built up. The angular acceleration alpha is rate of change of velocity, angular velocity with respect to time. So it will be, alpha will be dw by dt, which is d2 theta by dt2, and substituting the values of d theta by dt, we obtain this to be at over r, that is rate of acceleration is given by at over r. So the velocity, the linear velocity, can be written as, in terms of angular velocity, we can write it as v is equal to omega r. Omega is equal to v over r, and likewise at is equal to r into alpha, where alpha is the angular acceleration. The relations between angular distance theta and angular velocity omega and the linear velocity v have been already written in the earlier slide, but in the picture you can see that the theta, although it looks large for convenience of viewing what we are looking at, but in differential calculus, when we are trying to calculate these things, then we always consider a small distance covered. So for example, the dv is always equal to dx by dt, where here the x is considered to be small. Likewise, this theta is considered to be a small distance covered in the small time dt, and from there we have omega, the angular velocity, and the relationship that is developed. The Newton's second law requires that there must be a force acting in the tangential direction to cause angular acceleration. The strength of the rotating effect, called the moment or the torque, is proportional to the magnitude of the force and its distance from the axis of rotation. So it's very similar to the thing as F is equal to ma, only we write in terms of rotational terminology. The perpendicular distance from the axis of rotation to the line of action of force is called the moment arm, and the torque m, acting on a point mass m at a normal distance r from the axis of rotation, is expressed as M is equal to RFT, and that is then in turn equal to force is equal to MA. So it's RMAT is equal to MR square into alpha, and M is equal to integral over R square alpha into delta M, where M is a small mass. This can be written as I into alpha, where I is standard alphabet or notation for inertia of the body. If we compare the analogy between the linear and the angular motion, we see here that mass and moment are related to moment of inertia I. Linear acceleration A is equal to angular acceleration alpha. In the linear motion, if we have V, in angular motion we have omega. In the linear momentum, there corresponds angular momentum. So if linear momentum is mass into velocity, the angular momentum is inertia into angular velocity, which is omega. Force F corresponds to torque and is denoted by M. So these are the values that we have for these things. And unlike mass and rotational inertia of a body, that also depends on the distribution of the mass of the body with respect to the axis of rotation. So where the mass is distributed, where it is lying, that will take effect on the total inertia that is taking place on the body or the fluid motion. We denote here as I into W, the inertial effect, as H, and H is given by the integral that you see, and therefore M is equal to the angular momentum I into alpha, where I alpha is the angular acceleration, and angular acceleration is equal to d omega by dt, and this can be written as di of omega by dt, and I omega can be written as h. We normally write it as this, and therefore M can be written as dh by dt. So these are the same terms written in the same manner and reflected again in the form of a circle. Omega is normally turned, or theta, the angular motion, is measured in terms of radius. The whole circle is divided into 360 degrees, 2 pi radians, and the relation is given here for an angular velocity. And the same thing, angular velocity versus the RPM, that is a rotation per minute. This is a similar kind of thing. Essentially, the rotation, the angular velocity that is covered and related to linear velocity. These are standard terminology that we consider from time to time. So rotation per minute can be for the shaft that is rotating. It can be for the blades or the wheel that is under consideration. And the kinetic energy is given by half I omega square.